Everybody, today we are discussing the next topic, that is the retrosynthetic analysis. So the retrosynthetic analysis, as we discussed earlier, it is the reverse process of the actual chemical reaction. See here, for this compound, if you are doing the retrosynthetic analysis, we will get the charged fragments of the target molecule. So this is known as the synthons, and if you are developing the synthon, we will get the synthetic equivalent. So synthetic equivalent are the actual reagents or starting material for the chemical reaction. So retrosynthetic analysis means it is the reverse of the actual chemical reaction. Now we are moving into some of the guideline for the retrosynthetic analysis. So first is the disconnection must correspond to the reverse of the actual reactions. That is the definition of the retrosynthetic analysis. So if you we have to keep in mind this point while we are doing the retrosynthetic analysis. That process must be reversible, and according to that process we have to construct the target molecule by the same chemical reaction. So if it is not possible, the retrosynthetic analysis is not applicable for that type of retrosynthetic analysis is not applicable for the target molecule. So we have to convert in another way. That is, we have to do the retrosynthetic analysis by using the functional group interconversion, or we have to choose the other method for making that molecule. The second point is the compound which contain heteroatom disconnect next to the heteroatom. That means if a target molecule consisting of a heteroatom, so usually we have to follow that. We have to disconnect the bond which contain the heteroatom. So for example, see here, this is the retrosynthetic analysis of chlorobenzide. So here in this example, we have to see the three heteroatom or two different type of heteroatom, two chlorine and one sulfur. So according to our guideline, we have to disconnect at the heteroatom the bond which contain the heteroatom. So we have we have to see the three bonds here: CCl bond, 2 CCl bond and 1 CS bond. So where we have to disconnect? We cannot disconnect the CCl bond, because if you are disconnecting the CCl bond, we will get Cl minus and C plus. And the C plus exists in the phenyl ring. That's why we have to avoid the disconnection, because if you are creating the positive charge in the benzene ring, it is very difficult to convert into the reagent. That's why we cannot disconnect in the CCl bond here. So the other possibility is the disconnecting CS bond. So here we have the two CS bond. One is including the phenyl ring, the other is the benzene ring. So we have to disconnect this method. That means we have to disconnect CS bond containing the benzyl group. So we will get the two synthons here, Cl C6H5 S minus and Cl C6H5 CH2 plus. While we are developing the synthons, we will get the starting material, and this is the retrosynthetic analysis of chlorobenzide. Now we are moving into the third guideline. So before that, for the heteroatom, there are a lot of examples: esters, amide, ethers, amines, acetals, ketals and sulfides. Now we are moving into the third point. That means we have to avoid the chemoselectivity. That means we have to disconnect more reactive group first. We have already discussed the chemoselectivity. Chemoselectivity means if an targeted molecule contains more than one functional group, if we disconnect a one functional group, it will make some issues, because the other reagent, while we are synthesizing the same target molecule, the other reagent molecule will attack more than one functional group. That's why we have to protect some of this group, or we have to convert some of the functional group into other least reactive functional group. So that's why we have to avoid the chemoselectivity while we are doing the retrosynthetic analysis. Or the easy method is disconnecting more reactive group first. These are the guidelines for doing the retrosynthetic analysis of a targeted molecule. Now we are moving into the another example. This is the molecule of ICI D7114. If you are doing the retrosynthetic analysis according to the above guideline, the retrosynthetic is the analysis is the reverse of the actual synthesis. And here we have to see the two different type of the heteroatom, nitrogen and oxygen. So we can see the six different type of the bond which contain the heteroatom and the carbon, but we cannot do the disconnection in the CO bond because it will always generate a positively charged phenyl, and that is not possible, which are already discussed. And the other disconnection of the CO bond, that means other side disconnection of the oxygen, we will get a benzyl, that means PHCH2 plus synthon. So it is very difficult to alkylate that synthon. That's why we have to first disconnect in the CN bond. The one more point is that if you are disconnecting the oxygen, the ether group is a least reactive group while we are comparing the amine group. That's why according to this instruction, we have to disconnect the more reactive function group first. So the amine is the most reactive group. That's why we have to disconnect amine first. After that, we have to disconnect ether group. So if you are considering the amine, we have the two possibility. First is in the CN bond, which containing the large targeted molecule, or the other part, that is PHCH2 part. If you are disconnecting PHCH2 part, we will get a 2 fragment. So see here, if you are disconnecting in the D, we will get this 2 fragment, that is first is the PHCH2 plus and the remaining part is the other synthon, but it is we have to the alkylating the PHCH2 plus is very difficult. That's why we can avoid the path D and we can choose the path C, since other A and B follow the chemoselectivity. So that's why we have to eliminate, and C is the best method, and we have to eliminate D also. So this is the retrosynthetic analysis of this molecule. And next point is the function group interconversion. Function group interconversion means the name indicate that we are converting some of the function group into another. And what is the importance of this function group interconversion? We are doing the function group interconversion for the two important way to conduct the retrosynthetic analysis. First is we have to continue the retrosynthetic analysis, and we have to follow the same retrosynthetic analysis synthesis method, which is the reverse of the retrosynthetic analysis, to prepare the target molecule. For example, consider the retrosynthetic analysis of the benzocanine from toluene. We have two functional group here, that is the ester group and NH2. If you are disconnecting the ester, we will definitely get an alcohol and an acid. But here in the phenyl group, there is a two functional group is here while we are doing the disconnection. One is the carboxylic acid, the other is the amine group. But we cannot prepare this molecule because the acid and basic group is existing on the same benzene ring. So that's why it is very difficult to manage. That's why we have to functional group interconvert the NH2, most reactive NH2 group, into the NO2 by using the reduction oxidation. And after that we have to do the oxidation by converting acid to methyl group. And after that we have to disconnect into toluene. So this is the retrosynthetic analysis of the benzocanine, which is very important because in this chapter we have to study the retrosynthetic analysis of the benzocanine in a separate portion. So this is the retrosynthetic analysis. So after every retrosynthetic analysis, we should represent the synthesis. We should keep in mind that for every retrosynthetic analysis question, we have to first write the retrosynthetic analysis. After that, we should write the synthesis of the same targeted molecule. Now, next point is retrosynthetic analysis is used for creating some of the more active group. For example, if we have to synthesize a secondary amine by retrosynthetic analysis, according to our rule, we have to disconnect the CN bond and we will get a primary amine and a hydrocarbon. But if you are synthesizing the molecule by using the reverse of the retrosynthetic analysis, we will definitely get a tertiary amine, because if you are alkylating a primary amine, we will not get a secondary amine, but instead of that we will get a tertiary amine. That's why in this case we have to convert functional group interconvert to amide, converting the secondary amine to amide. After that we have to disconnect. So we'll get a primary amine and acid chloride. Then if we are doing the reverse of this retrosynthetic analysis, we can easily prepare the secondary amine. So similarly, we have to choose this method for creating the most hindered amine also. Now we are moving into the next topic, that is the one group CX disconnection. The point is indicating that one group, that is we are disconnecting only one group, that group is directly attached to the carbon atom of the targeted molecule. So this case is existing in the case of a CO, CN and CS disconnection. That means a heteroatom which is directly connected to the carbon atom of the targeted molecule. In that case, we are creating a nucleophilic displacement by SN1 or SN2 or carbonyl substitution with amine, alcohol or thiol or carbon electrophile. So the normal polarity of the disconnection will be cationic carbon synthons or an anionic heteroatom synthons, and represented by the acyl or aryl halide as electrophile and amine and alcohol or thiol as the nucleophile. So this is the one of the method for the CX disconnection. See the example. Rx will disconnect and we will get R plus and X minus. So R is positive charge and X is a negative one. So we will get the synthon as R plus and X minus. And if you are developing the reagent as R, X and HX as the synthons. For the example, if you are disconnecting a carbonyl compound by using the one group disconnection, that is CS disconnection, we will get RCO plus and X minus. We have to develop this molecule and we will get esters and HX. So this disconnection is known as 1,1 disconnection because the X group is directly connected to the carbonyl group. Okay. Now, sometimes the functional group which is attached to the